Hello, my name is Roy Simpson. I'm a professor of mathematics at Columbus River College in Sacramento, California. These are lectures on intermediate algebra, and this is a continuation of a lecture on graphing quadratic equations, the second part of that lecture. And the title for this one is basically the other 98%. What I mean by that is that we're going to concentrate on graphing quadratic equations that actually have an x term in them. In other words, well, this is a quadratic equation, and we're going to keep this as being non-zero. Okay, so we're going to have stuff like 3x squared plus 5x plus 1, or 3x squared plus 5x, or something like that. But all the other cases where we don't have a term with an x in it are treated in part A of this lecture. Now, to begin this lecture, which is for quadratics, probably the most important lecture you'll see for graphing quadratics, I want to introduce something that will seem very foreign to most people. Most people have never seen this style of graphing a quadratic equation, but I like to teach things that are more about common sense than about memorizing. So one thing I want you to note, actually a few things I want you to note. First thing, all quadratic equations, when we graph them, they graph as parabolas. And those are these objects right here, right? These kind of, some people call them V-shaped, some people call them U-shaped. I'd probably call them a U-shape as well. They're an ever-widening U-shape. Okay? They either open up or they open down, and later on in mathematics you deal with some that open left and right. But for now, let's just think about this, that they're all kind of these widening U-shapes. The second fact that I want to mention that should be common sense is that all parabolas must eventually hit the y-axis. And that might not be super common sense yet, but let's just take a look at a graph here, and I'm going to graph a parabola right here. Now remember, parabolas go ever wider. In other words, this keeps going out to the left. Eventually, it's got to cross this y-axis. It's just going to happen. Same thing if you graphed a parabola upside down. Let's say we graphed it way over here and it's very skinny. Even if it's very skinny, eventually it'll hit the y-axis. Eventually. So at some point, a parabola, it doesn't matter what the parabola is, eventually all parabolas must hit the y-axis. So that's something that I want you to kind of think about. Spend some time thinking about objects that just go ever wider like that. And you can probably convince yourself that they will all encounter or run into or intersect the y-axis. The next thing I want you to kind of think about is that all parabolas, since they have a U shape to them, if that U shape, and I'll graph this out kind of like this, you can think about this, pause it after I talk about it, whatever. But if this U shape attains a height of, let's just pretend this is a height of 5. Okay, so I don't know what the x value is, but I know this height is 5. That because it's a U shape, at some point in the future or in the past, if we're going backwards, it'll reach up to that height of 5 again. I just don't know the x value for that. I don't know the x value for that. But the fact is, it's a U shape. It's symmetric. If it reaches a height of 5, it should reach a height of 5 again. There's only one exception to this. If you're at the very bottom, you're not going to reach that very bottom again. In other words, there's no other point that reaches this bottom except for the bottom itself. But if you want to reach this height right here, well, there's a symmetric point over here. And in fact, that's what we call these. We call these symmetric points. So every point, except for the vertex, every point on a parabola has a symmetric point of symmetry. And by the way, that symmetric point can be found just by looking at this axis of symmetry. It's a mirror image, right? So you have to be at that height again. I want you to really think about that. If you say, oh, I totally get it right now, I promise you when we start doing examples that you might go, what the heck is he talking about? So I really need you to think about this, that, listen, you got a U shape. If it reaches 5 feet tall, then later on, it will have to reach 5 feet tall again because just going to curve down and come right back up. Probably the most important part of this, and actually the reason why I'm teaching this method, is that when you want to graph a parabola, you're really looking to graph the vertex, the lowest point or the highest point. In this case, with this parabola that I've drawn, since it opens up, it is the lowest point. However, if it opened down, I would be talking about finding the highest point. But anyway, finding that vertex is the most important thing when you're trying to graph a parabola. And in fact, for applications, that's always what we're looking for, almost always what we're looking for. So halfway between these symmetric points is going to be the axis of symmetry, where that vertex lies on. So if you take a look at this symmetric point at a height of 5 that we said earlier, and its other symmetric point, which is also obviously at a height of 5, halfway between these must be the vertex. It's a U shape. Halfway between any two symmetric points has got to be the vertex. So if I know, let's pretend for example that this x value is 0 and this x value here is 4, then I happen to know the x value for the vertex must be 2. It's halfway in between those two x values. All right. The only problem is we don't know the corresponding y value. And that sometimes is important in applications. It's very important in graphing. So the last step, really the fifth idea here, is that we're just going to plug this x value into the original equation to find out the y value. Now you should be writing this down. If you're in a class, my class, I don't care. It doesn't matter if you're in my class or somebody else's class, you should be writing this down. Just watching a video online is not going to educate you. What's going to educate you is you participating in this and actually thinking and trying to be a scholar, really, and educate yourself. So please write this down, have it available, because I'm going to just not refer back to these things. I'm not going to hop back to this. I'm just going to start doing examples and graphing a bunch of things. One thing I do want to mention, though, is that this method really is great if you have something of the form y equals, or I shouldn't say something, a quadratic equation of the form y equals ax squared plus bx. And then, you might have a c on there or not. It doesn't really matter. If you do have a plus c, that's good too. You could use it for that as well. But it's not good, really, if, so I'm going to put this in red. So don't use, if you have something like y equals just an ax squared, or y equals like an x squared plus k. Those are way too simple to use this method on. These are the simplest kinds of quadratics you can graph. If a is 3, it looks like the regular parabola, but it's it's stretched by a factor of 3. If a is 1/3, it looks like the regular parabola, but it's been compressed by a factor of 1/3. In this other case right here, if k is 5, it means it looks like the regular parabola. It's just been lifted up 5 units. Okay, those are very fast to graph. But these ones up here, let me go ahead and point at it with a green pen. These ones right here, not so much. Those are actually been shifted, and it's very difficult to figure out which way they've been shifted. In fact, let's go ahead and do an example here. Let's graph y equals x squared minus 12x. The first thing I'm going to mention is that this has got to have a y-intercept. It's a parabola, right? So what is the y-intercept? When are we going to hit the y-axis? That should be a question mark there. So the y-intercept, the reason why I like this method so much is that the y-intercept is the fastest intercept to get. Because all you need to do is to notice that on the y-axis itself, which is what we're asking where we hit the y-axis, on the y-axis all the x values are 0. So just let x equals 0. If you let x equals 0 up here, you find out that y is also 0. So I guess the y-intercept just occurs at 0, 0. And let me draw that in a different color, an annoying color. There we are. Now that we have that, and we've found that out, let's go ahead and ask ourselves, well, I know it's a U shape. It's like it might open up. Well, actually, it does open up because it's a positive number there. But I don't really usually talk about that. It's either opens up or opens down. But the fact is, it's a U shape. So if I hit the height of 0 at this point, then later on I should crawl right back up to the height of 0 again. Or I might crawl right back up to the height of 0 to the left, but it doesn't matter. The question is, when is the height, that's how I'm going to call it here, equal to 0 again? Because I want you to think about this in common sense. Like, listen, it's a U shape. When are we going to be at that height again? Well, you just go ahead and let y equal 0. All right, so here we go. I'll let y equal 0 in my original equation. And lo and behold, I get this beautiful result. I have a quadratic equation that I can solve because I know how to factor quadratics. I know how to solve quadratics by extraction of roots. In this case, it would be factoring. In fact, all these cases it would be factoring. So let's go ahead and see what we can factor out of the right-hand side. Both those terms have a 4 and an x in common. It leaves me with x minus 3. So it tells me I'm at a height of 0 again when that first object is 0, or when the second object is 0, or in other words, when x is equal to 3. Okay, I could play that game. So I'm at a height of 0 when x is equal to 0, but I already had that written in there. And I'm at a height of 0 when x is equal to 3. I'm at a height of 0 when x is equal to 3. Those are my symmetric points. Those 2 points actually exist on my parabola. Halfway in between must be the axis of symmetry, right? It's a U shape, so it's like we found these 2 points. So halfway in between has to be the axis of symmetry. So let me just write axis of symmetry, and remember, the axis of symmetry is a vertical line. So remember, equations for vertical lines are of the form x equals, and it's halfway in between 0 and 3. So it's the average of those two numbers, 0 plus 3 divided by 2, or in other words, 3 halves. I'm going to create a little dashed line here at 3 halves, which is 1.5. X equals 3 halves. And I know that's where the vertex is going to be. The vertex is going to be at 3 halves, comma, something. That something is a y value. I just need to plug in 3 halves into my original equation to find it. Well, let's see. Y is equal to, when I substitute in 3 halves here for x, I get the following. Well, let's see. 2 goes in that 12 6 times, so that's nice. And when I square this, well, I better just square it because I don't want to mess people up here. So this gives me 4 times 9/4 minus 6 times 3 is 18. And the 4 and the 4 will cancel, right? 4 over 4 is just 1. So that'll be 9 minus 18, which is a negative 9. Now, I didn't really leave a lot of room for a negative 9, so I'll just pretend as though that point right there is at a height of negative 9. Remember, the x value is at 3 halves, and the y value is at a negative 9. And now I have 3 points. Very easy to graph a parabola once you have 3 points. If you can draw straight on a digital board here. Something like that. So to recap what just happened, because you might just go, what the heck just happened? To recap, I just asked, when am I hitting the y-axis? Well, let x equal 0. Okay, we did that. We found out we hit the y-axis at 0. Okay, great. So I hit the y-axis at a height of 0. When am I at that height of 0 again? In other words, when can I be at that symmetric point again? So we let y equal 0 to find out basically when we're at that height of 0 again, and we solve the corresponding quadratic equation. You find out that it happens that the height is 0 for this parabola when x is 0 or x is 3. So That's what I plotted here. This is x equals 3. The height is 0. Halfway in between is the vertex. So I just found the halfway point between 0 and 3. That's pretty easy. That's arithmetic, right? And then I plug that value in to the original equation to find out what the corresponding y value is for the vertex. Now this may seem like a lot at first, but trust me, you get good at this, you can graph a quadratic equation in no time flat. Let's do a few more. This is an interesting one. Graph y equals 2x squared plus 4x minus 1. I always start just by asking myself, because I know it's a parabola because of the x squared, so I ask myself, when am I hitting the y-axis? So well, maybe I should say, when do we hit y-axis? Because it's got to happen. It's not necessarily true that we hit the x-axis, because we could have a parabola that looks like this. It would never hit the x-axis, but eventually it widens out enough to hit the y. So I don't really start by asking, when am I going to hit the x-axis? I always ask, when am I going to hit the y-axis? Well, that means let x equal 0. So I do that here. I'll let x equal 0, and I find out that occurs at -1. You know how easy that was? Cover up these things with x's, the terms that have x's in them, because they're just 0. I get y equals a -1. I'll plot that point. Let's pretend this is a height of -1, so it's 0, -1. And now I'm just going to ask myself, well, I want to know, where's the symmetric point? Is it to the right? Is it to the left? So when are we at a height of -1 again? It's such an important question. When am I going to be at that height again? It's like a roller coaster. Am I going to roll down and come right back up and it will occur here, or am I going to roll down this way and come back up and it will occur over here? That's an important question. So you let y equal -1 because you're asking, when am I going to be at height of -1? So go back to the original equation, let y equal -1. Now a lot of people get intimidated by this step because they think, oh man, I have to solve a quadratic equation. But guess what happens? And this always happens. This is not a fluke here. This always happens. I'm going to add, because I see I have two versions of x, two different powered versions of x, which means I have to move everything to one side of this equation. So I'm going to add 1 to both sides. And when I do that, I get this beautiful 0 is equal to 2x squared plus 4x. Notice there's no constant left over there. There's no constant term. That will always happen when you use this method. Both those terms have something in common. The 2 and an x. So I'm left with x plus 2. And this 2x times x plus 2 is equal to 0 when x is 0 or x is a -2. So in other words, I'm at a height of -1 again when x is equal to 0. Well, I already have that plotted. There's x equals 0, height is -1. Or x is -2. So I have my symmetric points. Halfway in between these points is going to be the vertex. So let me just label that on here. I'll just type, or I'll write in, vertex is going to be halfway between these two. The average of 0 and -2 is -1. So when you do this, you should really draw in an axis of symmetry that occurs at that halfway point. You should label it too. This is x equals -1. That's the vertical line there. And now all we have to do to find the actual height of that vertex is plug -1 into this equation. I'll do it over here. Y is equal to 2 times the -1 being squared plus 4 times the -1 minus 1. That's going to be 2 times 1 minus 4 minus 1. So that's a -3, I think, right? 2 minus 4 is a -2, minus another 1 is a -3. So I am, let me do the right color pen here, -3. So my vertex is at -1, comma, -3. 3. I'll say is right here, -1, comma, -3. Now I have my 3 points. I'll connect them up and draw my parabola. Okay. Now, something that I'm not going to mention in this lecture, but something that might be necessary for a future lecture, just to let you know, because I'm not really concentrating on finding x-intercepts right now. I really just want to know how to graph a quadratic equation. I don't really care about x-intercepts right now. I want to know about y-intercepts. The symmetric point halfway in between is a vertex. But later on, we'll talk about, in a future lecture, about finding these x-intercepts. But that's not my goal right now. I'm just going over the basics of graphing a quadratic equation. By the way, this is the best way I've found to graph a quadratic. There's, I don't think, a single flaw with using this method because it makes sense, right? Every parabola hits a y-axis, and every parabola, if you reach that height here, you got to reach that height again because it's a U-shaped curve. Halfway in between those hits is going to be the vertex. That's as simple as it is as far as thinking. Let's go ahead and do just one final example. I just want to show you that you can even use this method when you're graphing a quadratic equation with decimal coefficients. Maybe I won't make this my last one. I'll do one more beyond this. Just for those who are using the internet to search for how to graph quadratic equations, they might want to see one that involves an extra plus c here. So I'll do one more of those. Well, I draw my axes in, and I'll go ahead and mention right now that it's a parabola, right? There's the power of 2. And all parabolas hit the y-axis. So I'm just going to ask, when do we hit the y-axis? And that means, what is our y-intercept? So let x equal 0. What's nice about this method, there's so many things that are great about this method, but another nice thing about this method is I don't really have to deal with decimals that often here. When I let x equal 0, you see that y turns into 0. So that's a very nice result, that our y-intercept essentially is 0, 0. So I'll just graph that in there. Now I'm going to ask that question, because if we reach a height of 0 with this parabola, when are we going to reach that height of 0 again? When are we at height equals 0 again? I'm just quickly writing it. So if I'm asking you when my y values are 0 again, that means let y equal 0. And remember, the only reason why I'm letting y equal 0 is because of the fact that we found out we hit the y-axis at a height of 0. It's not that you always let y equal 0, it's that you let y equal wherever the value of wherever you hit the y-axis. We just happen to hit it at a height of 0. So when are we at the height again? Well, letting y equal 0, we get 0 is equal to 2.3x squared minus 10.8 x. In this case, I don't want to factor these decimals, but I do want to factor out the x at least. So I'll factor out an x. I'm left with 2.3x minus 10.8. In other words, I'm at that height of 0 again when either x is 0 or when, from this, x is equal to 10.8 divided by 2.3. This is horrible notation. I'm just letting you know. Usually you do not want to have the notation of decimals inside fractions, because fractions are defined to only have integer numerators and integer denominators. So instead, I'll go ahead and use a calculator here. Because these are given to me in decimals, I might as well use a calculator to do the division. So I just grab my handy dandy graphing calculator here, and I find out that it's this horrible number. Alright, but I'm going to keep that number available. It's 4.7 roughly. So Let me just say it's approximately 4.7. I can still do the math even though I have an approximate number. Now, remember, I'm asking when am I at a height of 0. So that occurs at x equals roughly 4.7. So I'll just put that in here, 4.7 comma 0. Halfway between these 2 points is going to be my axis of symmetry. I'll graph that in purple here, halfway in between. That looks almost halfway. I kind of went a little bit too far to the left there, but whatever. And remember, it's a vertical line, so it has an equation x equals. And it's halfway in between 4.7 and 0. I'll go ahead and drag the calculator over and just say divide that last number by 2, because that's really the halfway point. And it looks to be about 2.35. So I'll write that in there. 2.35. That's very roughly. We've approximated that value. But still, it's okay. Because I now know my vertex is approximately, I'll write that in, vertex is approximately 2.35 is the x value. And now I just need to find the y value. And because I have a calculator right here, and I have this number already ready to go, I'm going to go ahead and teach you, if you have a graphing calculator, teach you how to store that number. If you don't have a graphing calculator and you can't store it, well, you're just going to have to basically say what's 2.3 times 2.35 squared minus 10.8 times 2.35. For those who do have a graphing calculator, I'd like to teach you a trick. If you get an answer and you want to keep it, you can hit this STO button. That means store that, please. And you have to select a letter you're going to store it as. Well, you have every letter of the alphabet available. I don't know why, but I would just probably avoid using X. I usually just store it as A. So to access the letters, you use this alpha button. Click alpha and you get this blinky little A there. And now anytime I press a key on this keyboard, it'll actually replace this blinking cursor with the letter associated with that key. So if I want A, I'll just hit the button that has the little green A above it. So I've stored that answer as A. Now what I'm going to do is find out what 2.3 times A squared is. 2.3 times, technically you don't even need the times, A squared. Well, remember to get the A, it's alpha and then A squared minus 10.8 times, again, alpha A. Notice the same format, right? 2.3x squared minus 10.8x, 2.3a squared minus 10.8a. And you get a negative 12 point, and I'm just going to round to the nearest tenth here. Let's go negative 12.7. That's pretty far down there. So I'm just going to pretend as though it's right about here. And that's 4.7 comma negative 12.7. And I should probably write that in also here, negative 12.7. Now once I've done that, I can actually go ahead and graph the rest of my parabola. Wow, that's the best curve I've done all day. And I will mess it up by doing that. Okay, it's supposed to be symmetric, but it's a little bowed on that side. Okay, and there we have it. We have our parabola graphed. Even though it's some messy looking numbers, it gets graphed. Now to show you the power of this method, I'm going to do one last example. And this example I'm going to do at near to full speed. And it's going to make up a problem. And I'll choose ugly numbers too. I'm going to basically, because I can go any speed I want, you can pause the video. So I'm going to make up just some ugly numbers here. Graph y equals a negative, let's do 1/3 x squared minus 2/5 x plus, let's do a plus, I don't really care, plus 4. Let's do a plus 4. All right, so I'm about to go full speed. Let me just get my pens working. I know it's got a y-intercept, so y-intercept let x equal 0. Y will be a positive 4. I'm just going to quickly graph my axes by, maybe I'll use a larger chisel on this one. Here's the x-axis, here's the y-axis, label all that stuff. Go back to my regular old chisel here. And I said it's at a height of 4, right? So 1, 2, 3, and 4. So it's 0, 4. There's my y-intercept. Now I'm just asking, when am I at that height again? Well, that occurs, wrong color pen. That occurs when y is equal to 4. I just want to know, when is y 4 again? Technically, it would be much faster than this even. I'm going to subtract 4 from both sides to start getting everything on the right hand side. And lo and behold, I get 0 is equal to a negative 1/3 x squared minus 2/5 x. Notice there's no constant left. Great. Let me factor this. Pull out an x. That's all I really care to pull out. And it turns out that I'm at a height of 4 again when x is 0 or when this junk in here is 0. That's going to take a little bit of solving for me. In other words, when negative 1/3 x is equal to positive 2/5, multiply both sides by a negative 3 and you get x is equal to a negative 6/5. Okay, that tells me that this point right here occurs at x equals negative 6/5, comma 4, right? The height of 4. So it tells me I'm at a height of 4 at when x is 0 and when x is negative 6/5. Halfway in between is the axis of symmetry. Just draw that in here. Doop, 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 doop. Great. Well, let's see. Halfway in between 0 and negative 6/5 is actually negative 6/10. I just multiplied the denominator by 2. That's all you really have to do. That's what half of a number is multiplying the denominator by 2. But I'd like to reduce this fraction, so they're both divisible by 2 there. It's negative 3/5. All right, so I know the axis of symmetry is at negative 3/5. The hardest part really is this last part. It's finding what the y value for the vertex is. So I'm going to plug in negative 3/5 into my equation. This is really the lengthiest part, but you'd have to do this no matter what method you use for graphing. So let's see, we have negative 1/3 times 9/25. Let's see, plus 6/25. Plus, and since everything looks like it's going to have 25s in denominators, I'm going to change this to be 125ths. Which equals, let's see, 3 goes into 9 3 times, so that's a negative 3/25 plus 6/25. That's going to be 3/25 plus 125, which is going to be 103/25. That does not reduce. So 103/25, that's a little bit over 4 actually. So I'm just going to go ahead and plot that right about here. That's just slightly over 4. And I'm going to label it first of all. So that occurs at x equals a negative 3/5, y equals 103/25. And now I'll connect these with a nice smooth curve. I'm having a hard time doing that. Make sure if it starts wide, you keep it wide. Don't make it just all of a sudden flop down. It should make sense that it's opening down though, because it has a negative coefficient on the x squared. That means it opens down. I can't resist. I just want to do one more at full speed. So I will do just one more at full speed. You can always just stop this video, right? So it doesn't really matter. But I just can't resist. I really love graphing using this method. Ridiculous, isn't it? So graph, and this time I'm not going to make it so ugly. I'm just going to show you the power of it if you go quickly. 3x minus, I'm just going to make my life easy. Oh, this should be 3x squared minus 12x plus, no, let's go minus 2. Okay. So y-intercept occurs at 0, negative 2. I'm at that height of negative 2 again when this is true. But I know right now that if I add 2 to both sides, I'll get this. I'm just going to factor here 3x times x minus 4. That tells me that I'm at the height of negative 2 when x is 0 or x is 4. Halfway in between is the vertex. The vertex will occur at halfway between 0 and 4 is 2. And I can plug 2 in to find the y value for the vertex. I don't even want to go through all that. 2 squared is 4 times 3 is 12. Minus 2 times 12 is 24. Minus 2, that's a negative 14. Oops, well, shoot. Negative 14. And so now I will graph everything out. Label as much as possible x, y. Let's see. My y-intercept is at a negative 2 here. And in fact, because I already know my vertex is going to be so low, I'll say that negative 2 is actually right here. So my y-intercept is right here at negative 2. And then I reach that height of negative 2 again when x is equal to 4. 0, negative 2. Halfway in between is the axis of symmetry. I'll just quickly draw some large dashed line for that. That happens to be at x equals 2. And we plugged in 2 to our equation and found out that the vertex occurred at 2, negative 14. Connect the dots with a nice curve, hopefully, and we're done. All right, that's it. Do this all day long. Make up as many as you want. It's very easy to do once you get it.